Hello everyone, my name is Aaron Stannard. I'm the Chief Technology Officer of Petabridge, a company that provides training, support, and consulting for Akka.net. And today this is going to be one of the first of our internals videos, where we explain how some of the components built into Akka.net actually work under the hood. And we're going to talk about Akka.remote and how it actually establishes connections to remote actor systems. So for those of you who aren't familiar, Akka.remote is the module that powers all of the networking capabilities that Akka.cluster and a lot of the other modules actually use. So understanding how Akka.remote works is pretty fundamental to building distributed systems on top of it. So we're going to start by taking a look at some configuration options for two systems we're going to have talk to each other. So here's a sample configuration. We have two systems, System 1 and System 2, and we're going to have them use Akka.remote to communicate with each other. So the first thing we need to do to enable remote communication is make sure that both systems set their actor reference provider to be the Akka.remote remote actor ref provider. This actor ref provider, when it gets initialized, is what boots up all the remoting capabilities we actually need. So both actor systems need to have this enabled in order to communicate. Next, we're going to go and open the remoting section of this configuration file, and we're going to specify some options for the Helios.tcp transport. So Helios is a reactive socket programming library that Akka.remote references, and it enables both TCP and UDP communication. In this example, we're going to enable the Helios TCP transport, and System 1 will connect to a TCP socket on port 8080 on localhost, and System 2 will bind to a socket on port 8081 on localhost. Talking about how sockets work is a little beyond the scope of this video, but we'll do some Helios internals videos in the future too. So let's start by taking a look at some of the terminologies that Akka.remote uses internally. So first is the concept of a transport. A transport in the context of Akka.remote is a literal network transport. So a Helios TCP connection is the default transport that most applications use. However, you can have multiple active transports. So you can have a user-defined transport that uses a protocol that's not supported by Helios, or you could even have a Helios TCP and a Helios UDP transport active at the same time. But the one important distinction to make is you can only have one instance of a TCP transport open at any time. Next, we have the concept of an endpoint. An endpoint is a specific address binding for a transport. So when we bound Actor System 1 to localhost at port 8080, that created an inbound endpoint for that TCP transport. In order for an endpoint to exist, we need to have a valid transport in order to do that. Next, we have the concept of an association. You can think of an association as a connection between two endpoints. One endpoint on one actor system and another endpoint on a second actor system. And these actor system associations depend on having a valid inbound endpoint and a valid outbound endpoint. And we'll talk a little bit more about what those terms mean in a second. And finally, we have the notion of an association handle. Association handle is a service provider interface between the network transport and the actors in your actor system that actually receive those messages from the network. So the association handle is used by the system actors built into Akka.remote. Your actors that you define as an end user don't see the association handle or really any of these components at all outside of the configuration that we created earlier. So let's take a look at what the initial state of an actor system might look like. So in the initial state of our actor system, we have two independent systems that each occupy their own process. They might boot up around roughly the same time, and the first thing they're going to do once the actor system initializes its actor reference provider is they're going to open all of their configured transports on their appropriate ports. So they're going to open an inbound TCP endpoint on port 8080 for actor system 1, and an open inbound TCP endpoint on port 8081 for actor system 2. And this transport will begin listening for incoming associations. So at this point, neither actor system is connected to each other, but they both have the ability to receive inbound communication attempts from one actor system or the other. So let's talk a little bit about how we actually connect to a remote actor system. So when we want to connect to a remote actor system, we have to either send a message or try to deploy an actor to the remote actor system we want to connect to. And we do that by using a fully articulated actor path, just like in the example on this slide. So we're all familiar with the path part on the right that represents an actor's position on the hierarchy. But let's talk about the left-hand side of the actor path. So we have the name of the actor system, which is pretty obvious and straightforward. But what's less obvious is what happens to the Akka protocol when we start enabling transports. So if we turn on the Helios TCP transport and we want to communicate to a remote system that's also using TCP, we add the .tcp extension to the Akka protocol at the very front. So all of those actors can be addressed to via the protocol akka.tcp. If we enabled UDP, that might be akka.udp. And then we have the address, which follows the name of the actor system. The address represents the inbound endpoint to which that actor system is listening on its protocol. So if we're trying to connect to actor system 2, a full actor path might look like akka.tcp, mysystem at localhost 8081 /user/actorname1. Let's talk about the distinction between inbound and outbound endpoints. So if System 1 attempts to send a message to System 2, System 1 will create an outbound endpoint. System 2 will receive this message on port 8081, and it will receive it on its inbound endpoint. So the importance between these two distinctions is that an outbound endpoint begins in a different state in the association process than an inbound endpoint does, because the inbound endpoint already knows that the other endpoint on the other end of the connection is there and listening. So that is something that we're going to have to bear in mind when we start talking about the Akka protocol in a little bit. So let's go and walk through the association process. So System 1 and System 2 are both up and running. They have their TCP transports bound to 8080 and 8081 respectively. And we need to go and create an outbound endpoint from one of these systems to the other. So System 1 is going to attempt to send a message to System 2 over TCP on localhost 8081. And in order to do this, we need to create a new outbound endpoint. So what will actually happen under the hood with the Helios TCP transport is we'll open a new TCP connection on a random free port number that the operating system provides. So we go and open up a new TCP connection, and we send a handshake message over it to System 2 once the TCP connection is open on the other side. System 2 will receive the handshake message from localhost random, because that random is the number of the outbound port on the outbound socket. And we will accept this inbound association, and we'll send an associate message back to System 1 on its outbound endpoint, and the connection will be established at this point. So let's walk through the details of the Akka handshake protocol in a little bit more detail. So on either side of the handshake protocol, we have two state machines, and these are modeled using what's called the protocol state actor in Akka.net. And this is part of the system actors that are invisible to you as an end user. So we have these two state machines, and System 1, during this process we just walked through, will have a user-defined actor attempt to send a message to System 2 over TCP. So that's the first step in creating the handshake, is someone attempts to send a message to some actor system. So System 1 will check to see if there's an available endpoint to System 2 already. If we have an open association, then we can already communicate with System 2, and we don't need to go through the handshake process. So since there is no endpoint available, we need to create one. So we're going to create a brand new protocol state actor, and we're going to put it into the closed state on the outbound side of the connection. So once the actual transport is able to open a socket connection to System 2, we're going to shift from being in the closed state into the wait handshake state on System 1, and we'll send an associate message over the network to System 2. System 2 already has a socket connection open and waiting, but it hasn't created a protocol state actor yet. The endpoint manager, an actor we're going to talk about a lot, receives the associate message and checks to see if it's quarantined to System 1. We'll talk a little bit more about what that means in a minute, but if it hasn't quarantined the node, we can accept this association attempt. So System 2 will create its protocol state actor initially in the wait handshake state, because it already knows that System 1 has an outbound protocol state actor that exists based off the fact that this association message was sent from it. So when we check to see if the quarantine exists, and if it doesn't, then the inbound side of the connection can shift into an open state, which means that it's able to receive and send messages from user-defined actors to System 1. So it'll send an associate message back to System 1 in order to complete the handshake. System 1 will check to see if it hasn't quarantined System 2. And quarantining can happen if something goes wrong during this handshake process. But if there hasn't been an issue, it'll accept the associate message from System 2, and it'll complete the handshake process. And now the connection is open on both sides of the protocol. So why do we bother with this handshake process? Well, there's a two-part explanation to this. First, if you're familiar with the TCP protocol, you know that there's already a handshake built into that. So why do we have the need to do this again? And the reason is because we need to guarantee connection-oriented behavior over any type of transport, including connectionless ones like the UDP protocol. And the reason why we need connection-oriented behavior is because actor references depend on being able to guarantee that they existed at some point in the past in order to be created. So, the only way we can really do that reliably is with connection-oriented behavior, where we are able to tell at any given time that both ends of a connection are active and receiving messages. So the handshake protocol is able to establish that the other end of an association really does exist. Then we have a system of heartbeats that get sent back and forth over the network after the association is made that's able to guarantee that connection is still open, even on systems that aren't connection-oriented like UDP. So that's why. We're not going to talk very much about the heartbeat system in this particular video, but we will address it at some point in the future. Okay, so let's talk about the remoting system actors that power Akka.Remote. So first we have the System Guardian. You may notice that every time you create a user-defined actor in one of your applications, the path begins with /user. That's because all of your top-level user-defined actors are actually children of the User Guardian. Well, all of your top-level system actors that are built in are children of the System Guardian. Same idea, but these are just for actors that are built into Akka.net. So the first of the remoting system actors we want to talk about is the Transport Supervisor. This actor is responsible for supervising the underlying network transport and restarting it in the event there's a critical failure there. And the Transport Supervisor creates an Akka Protocol Manager. The Akka Protocol Manager's job is to create protocol state actors for every endpoint that is attempted to be created on top of that transport. So for every inbound and outbound endpoint, there exists one protocol state actor for that transport. And the Akka Protocol Manager's name includes the scheme of the underlying transport. So if we were to have a TCP transport, then the Akka Protocol Manager would be called Akka Protocol Manager.tcp and then the UID. The UID represents the ID of that transport in the event that it needs to restart. So every time that UID changes, effectively you're connecting to either a new instance of the transport. And that factors into some of the decisions that are made by the Endpoint Manager, the next actor we're going to talk about. The Endpoint Manager is effectively the most important actor in Akka.Remote. And we're going to spend the next couple of slides going into some more detail on what it does. But the important thing you need to know is that the Endpoint Manager is responsible for the creation of endpoints. So whenever we create an outbound endpoint, the first actor we create is what's called a reliable endpoint writer. This is an actor that has some built-in behavior for being able to do guaranteed delivery of messages over the network. So it's responsible for making sure that all the messages needed to create an association actually do arrive at their destination with some moderate amount of effort and retry first. Then there's the endpoint writer. This is the actor that actually represents the writable end of an endpoint. So any messages you want flushed onto the network are delivered via the endpoint writer. And then there's the endpoint reader, which, as you might have guessed, reads messages from the network. So both the endpoint writer and the endpoint reader communicate directly with the association handle that allows us to link directly to that transport. So we're going to talk a little bit more about all of these actors next. We also have the remote daemon. The remote daemon is responsible for the remote deployment of actors. So actor system 1 actually has the ability to serialize props for an actor and deploy it on actor system 2, as long as actor system 2 actually implements the class that is specified as part of that deployment. So the remote daemon is responsible for creating remote actor references and for killing them in the event that the network disassociates. So the remote daemon is a pretty special actor, and we're not going to talk about it much more in this presentation, but we might do a subsequent video on it for people who are really interested. And then next we have the Remote Watcher, which takes the Death Watch capabilities that are well defined in Akka and extends them so they can work across the network. So a actor on Actor System 1 can receive Death Watch notifications from an actor on Actor System 2. And in the event that the network goes down, it will receive a Death Watch notification. So it'll say, okay, as far as we're concerned, that actor's dead, so we can't guarantee its existence anymore. So that's what those two actors do. So we're going to talk about the Endpoint Manager in a little bit more detail now. The Endpoint Manager has a lot of responsibilities. The first is that it's responsible for starting all of the underlying transports. So even though the transport supervisor supervises them from that point onward, at the very beginning of the Actor System boot process, when Akka.remote is enabled, the Endpoint Manager is the actor that actually starts all of those transports and binds them to their sockets and sets up the initial inbound endpoint. The Endpoint Manager is also responsible for applying policies to each endpoint. So if we have an actor system that has been downed at some point in the past, we may not want to connect to it again because there might be something that's wrong with that machine or that process, and we might require that that system reboot before we can reconnect to it. We'll talk a little bit more about policies on the next slide. And the Endpoint Manager is also the first responder to all inbound association attempts. So anytime someone attempts to establish a connection to any given actor system, the Endpoint Manager makes a decision based off of its policies of whether we're going to allow that association attempt or not. And once the association attempt is allowed through, it hands that off to the Akka Protocol Manager. The Endpoint Manager is also responsible for creating the Endpoint Writer and the Reliable Delivery Supervisor. And as we recall from the previous slide, the Endpoint Writer is what actually creates the Endpoint Reader too. So the initial right side of the the initial right side of the endpoint, which is what we need to complete the handshake process, is actually created by this actor. So the Endpoint Manager is also ultimately responsible for supervising these actors. So in the event that an endpoint disassociates, it's also the Endpoint Manager's job to figure out what to do about it. So that's the Endpoint Manager's responsibilities in a nutshell. Let's talk a little bit about its policies. So the first policy, and the one that we want, is the policy of pass, which means that we're okay, we can connect to this transport. We can accept this association from this remote system. The next policy is a gated policy, and this happens when a node shuts down. So it's usually a planned termination, at least to some extent. It means that there was a clean shutdown attempt. And we will block all connections to reconnect with this node until a retry window elapses. So that retry window can be configured, but it's typically 5 seconds by default. So this is just to prevent us from trying to rapidly reconnect to a system we know won't be available for a little while. That's the purpose of gating a connection. Now quarantining is a little different. You really want to avoid a quarantine connection. That means that during an association, the node somehow failed to complete the handshake process. So there's something effectively wrong with that transport or wrong with that machine, or there's something going on with the application that's using it. And so we require that the application must be restarted with a new UID before we'll accept a connection from it. We won't establish outbound connections to a quarantine node, but we'll accept an inbound connection from that quarantine node if the UID is different, because that means that the actor system is rebooted. And the quarantine window will elapse after a period of time. We'll disable the quarantine if enough time passes, and that can also be configured too. So let's actually see what the process of interacting and reading and writing with endpoints looks like. So let's talk about writing to endpoints. So the first thing that happens is a user-defined actor wants to send a message to a remote actor reference or to an actor selection that sits on a remote system. Or maybe we want to remote deploy an actor, in which case that's really going to be done as a message that's addressed to the remote daemon on the other machine. That'll be transparent to you. The endpoint writer receives that user-defined message, and it'll serialize that message and write it to the association handle. So we use a combination of Google protocol buffers to create an envelope with some important metadata, and then we have a little blob of binary JSON that actually contains your user-defined message. So the metadata that's included on that serialized message includes things like which actor this is going to be delivered to, and what's the path of it, and so forth. And then the association handle actually writes that serialized message to the network transport. So that's what writing to an endpoint looks like. So reading from endpoints, as you might imagine, works the opposite way. A message arrives from the network, and the association handle and the underlying transport will push that message into the appropriate endpoint reader. So this is a reactive system. We don't have to pull for messages. They're pushed into us. So the endpoint reader will receive that message, and it'll deserialize the message and find the recipient. So it'll go and figure out which actor should receive this message. And if no actor can receive that message, let's say it's an actor selection for an actor that doesn't actually exist on the system, then it'll send that message to dead letters. Once it does find a valid recipient, though, it'll use a special class called a message dispatcher to actually send that message to the recipient. So that's what reading and writing from endpoints looks like. So let's talk about the process of disassociation, which is how remote communication between two actor systems ends. So we have an open association between System 1 and System 2 in this example. System 2 crashes, has an unplanned termination. So when the System 2 crashes and the process is terminated or restarted, the association is automatically closed because the socket connection that was powering the transport is now closed itself. So the transport disconnects, so no more messages will be received. And when that transport closes on the System 1 side of the equation, it'll go and create a disassociation notification for the endpoint manager. So it'll propagate that message to the endpoint manager, and the endpoint manager will kill all remote deployed actors from System 2. It does this by communicating with the remote daemon, and any further outbound messages that are intended for System 2 will automatically be delivered to dead letters. Now, the endpoint policy that the endpoint manager will apply to System 2 going forward will depend on the manner in which this crash occurred. An unplanned termination won't result in a gated policy. We're going to wait for that system to come up, and we'll attempt to connect to it again after some period of time. But if System 2 is a planned termination, we'll go ahead and buffer our connection attempts for 5 seconds by default, or some configurable amount of time. And in the event that we attempt to reconnect with System 2 and we disassociate then we might quarantine that connection until the process has had a chance to reboot. So that's what the disassociation process looks like. So that's it for this video. Thank you all for watching. And if you want to learn more about Akka.Remote and how to use it in your own applications, we encourage you to check out Petabridge's virtual training. So these are half-a-day-long live webinars with myself and Andrew, and we'll teach you some of the ins and outs of Akka.Remote so you can better use it in your own applications. So check out the URL on the bottom of the screen and give it a try. Thanks for watching.